All right, so we have a single point charge, and this question is asking us, what is the electric field in component form at point 2 in the figure? Okay, so electric field, this charge is creating an electric field all around it. We're only asked to find this field at one point. Now, we always want to draw the field at the point we're asked about. So I drew arrows to represent that the electric field will be pointing away from this positive charge. So at point 2 over here, away is going to be up and to the right. So this is the electric field that we're looking for. Okay, the equation to calculate electric field due to a point charge is kq over r squared, and then r hat is representing the direction that it points radially away. We will want to put that in terms of x and y components, though, in terms of a coordinate system that we would be using. So K is our constant, and it has units of Newton meters squared per coulomb squared. Q is the amount of charge we have, which we do want in coulombs, so that this will cancel with one of the coulombs. R is the straight line distance between the charge and the point where we want to find the electric field. From the dimensions of this rectangle they've given us, 3, 4, this would be 5 centimeters. If you don't happen to remember that, you can totally do the Pythagorean theorem to solve for it. We want this distance to be in meters, so that when we square it, these meters squared will cancel with those meters squared. So this portion is going to be simply the magnitude of E, just how strong the electric field is at that portion, at that point. All right. 3.596. Again, I'm taking it out of the decimal places because I'm not at my final answer. The units, since we canceled both meters squared but only one of the coulombs, the units here for electric field are newtons per coulomb. Okay, so we have the magnitude that represents the length of this vector. 3.596 times 10 to the 4 newtons per coulomb. But this vector has x component and a y component. Now usually I draw myself my little triangle. Here's my x component. Here's my y component. So I need to find these components. Okay, to do that, I need to think about this angle right here. That angle is the same, let me draw, as the angle down here. That means I can figure out this angle from the dimensions of the rectangle. So the angle, I can say the tangent of the angle would be 3 over 4. So the inverse tangent of 3 over 4 is 36.87 degrees. So E sub x is going to be the magnitude times the cosine of theta, because that's the side adjacent to the angle. E sub y is going to be E sine theta. So the magnitude times the sine of the angle, because it is opposite. Now, writing out our vector. I'm going to just write that out first, and then I'll plug in the numbers. So this x component in the x direction, this x component, it is e cosine theta. The y component is e sine theta. Those are both positive directions. Because they both have E, meaning the magnitude of the electric field in them, just for writing stuff out sake, I'm going to plug it in this way so I don't have, that is silly, I know. Don't have to write out E multiple times. I know that was absolutely silly because I wrote out something else instead. But whatever. I do silly things at times. Okay. So calculating this through, I will write out my electric field. It looks like we have 2 sig figs, so I will also round it as I go. So that times the cosine. 2.9 times 10 to the 4th I hat. Plus 2.2 times 10 to the 4th j hat. If we wanted, which we don't need to, but we could factor out the 10 to the 4. Since they both have that. But we don't need to. We could also use a prefix and write it in terms of kilonewtons per coulomb if we wanted. Either way, this is the electric field at point 2 in terms of its components. We call this also vector notation. So this just represents how that 10 nanocoulomb charge is influencing the region of space around it. And knowing that, we could come and bring in any charge we want, put some sort of Q here, and we could easily find the force on it. Because the force on a point charge in an electric field is that charge itself times the electric field at that location.